In this video, I'm going to go through a quick outline of a derivation for the influence functional, which is something that we're going to need in order to track the state of an open quantum system using numerically exact tensor network calculations. A brief bit of motivation, we're going to consider that we've got an open quantum system, S, and it's surrounded or enveloped within some bath B. And the state of this composite system, so the system and the bath, is given by this density operator rho, and it lives inside the tensor products Hilbert space of the system and the bath. And what we want is the reduced state of the system. So we're typically not going to care what the bath is doing, we only care about the system. And the way that we can do this is by taking the composite system state and taking the partial trace over the bath degrees of freedom. And then this reduced system state is going to live inside the Hilbert space of the system. So one way that we could do this is we could derive an approximate master equation for the reduced state of the system. And then we could track the dynamics through that approximate master equation. But right now we're not interested in making approximations at the level of the physics. We don't want to assume anything about how the system and the bath interact. So instead what we want is to use numerically exact tensor network calculations. And the reason that we want to use these instead is because they don't require us to make any assumptions about what's going on between the system and the bath. So for example, in order for us to derive a master equation using perturbation theory, we need to be able to perturb about some small parameter, which usually is going to be, say, the interaction strength between the system and the bath. But if that interaction strength is strong, then we can't use one of these weak coupling master equations. And we don't want to have to worry about deriving different master equations for different situations. This is why we use these numerically exact tensor network calculations, because we can apply them in many different parameter regimes. So they're a bit more universal. So now we're going to go through a little bit of setup for this derivation. So the composite system state is closed and therefore evolves unitarily, where the unitary operator is simply given by the exponential of the Hamiltonian of the total system. So we're considering a time-independent Hamiltonian of the closed system here, but this would all work with a time-dependent Hamiltonian as well, but that would require a lot more writing. So I've just stuck with a time-independent Hamiltonian here. And I'm actually going to write this Hamiltonian in a slightly different form than we're used to. So normally for open quantum systems, we would see the total Hamiltonian is the system, the bath, and the interaction Hamiltonians. But instead, what I'm going to do is I'm going to write the free Hamiltonian of the bath and the interaction Hamiltonian as a single term, which I'm just going to call HB. And that means that my total Hamiltonian is the system Hamiltonian plus this HB here. So we just need to remember that the interaction term lives inside this Hamiltonian as well. The next step that I'm going to do is discretize my time axis. So I'm going to take my continuous time axis here, and I'm going to chop it up into a bunch of steps of size delta. And if I consider the unitary evolution operator u to the time t sub n, what that's going to be is n of these time steps of length delta. And each time step along this time axis that I've discretized, I'm going to label with some subscript k. So the next thing that this allows me to do is it allows me to break up my unitary operator. So if I want to perform the unitary operator u of t sub n, that's the same thing as applying the unitary for n delta time steps. And then I can simply take this factor of n out of the exponent and raise it to the power of n instead. So I now have n copies of the unitary operator u delta instead. So it's sort of like, instead of the unitary operator taking me from 0 to t, it takes me in small jumps along the discretized time axis instead. And the reason that I do this is that if I choose delta small enough, I can use symmetric Trotter decomposition, which means that I can break up this unitary which acts on the system and the bath, and I can decompose it using Trotter decomposition into an operator that just acts on the system, one that acts on both the system and the bath, and another operator that just acts on the system. And then I get some order delta cubed error term. So the smaller the delta is, the smaller my error is going to be, and the better my symmetric Trotter decomposition is going to be. So there's going to be some balance between reducing the time step in order to make our calculations have smaller error, but then obviously the smaller the time step is, the more computationally demanding our calculations are going to be. The next step that we need to do is think about the operator that the system interacts with the bath through. And I'm going to call this operator S, and I'm going to say potentially this operator might change in time. And since I've discretized time, I'm now going to label my operator with K. And remember that K just labels the different time steps along the time axis. So here I just spectrally decompose this coupling operator for the system. And then this lets me resolve the identity at time step K using the eigenstates of this operator, this coupling operator, sorry. And now we introduce a little bit of a weird notation, which is that superscript plus and minus represents putting these states on either the left or the right of the density operator. So if one of these states has a plus in the superscript, that means that it's been put on the left-hand side of the density operator. And if it has a minus, it's been put on the right-hand side of the density operator. And so I'm not entirely sure what goes on here, because we said that we don't want to make any approximations, but we have to assume two things about the system and the bath. And the first one is that at t equals 0, the system and the bath are uncorrelated. So their state can be written as a tensor product. And the second thing that we assume is that the bath starts off in a thermal state. So rho b naught is just equal to the Gibbs state with respect to the free Hamiltonian of the bath. And just for clarity or for continuity, I'm not going to write the brackets 0 on this bath state. Okay, so our goal in open quantum systems theory is to find the reduced state of the system at a specific time. So what I want is this thing here, right? But if I have an orthonormal basis, which the eigenstates of the system coupling operator form, then I can just find the different elements of this density matrix with respect to that basis, and I basically just found the state. And the thing that we want to show in this derivation is that the matrix element of this reduced density operator at time tn with respect to the eigenstates, with respect to the orthonormal basis formed from the eigenstates of the coupling operator at time tm is given by this path sum here. So this is it's a path sum. It's basically related to the Feynman path integral formulation of quantum mechanics. And now we'll see what the different terms mean. So this F term here is essentially just due to the free propagation of the system due to its Hamiltonian, which we see here and here. And notice that it's just a product of numbers, right? We've got these states, these bras and these kets on either side of this unitary operator, just basically making it into a number. And here we've just got this delta k. It can equal two different things depending on the value of k. Not super necessary right now. And then this term here is the thing that we're interested in the most, which is the influence functional. And again, notice that it's just a product of a bunch of numbers. It's the expectation value of these things with respect to this bath thermal state. And then this final term here is just the density, the initial density operator. That should actually have a subscript for S, sorry. That's just been transformed by this system Hamiltonian for half a time step. So why do we want to do this? Well, it turns out if we just move into the interaction picture, then this free evolution just disappears. And then that means that I can find the density operator of the system at any time by simply applying the influence functional to this slightly modified initial state. So if I can find my influence functional, I can find the dynamics of my reduced system in the interaction picture. So how are we going to do this? We're going to use a slightly modified or maybe just discretized version of Feynman's path integral or path sum. And essentially all that we do is we just resolve the identity a bunch of times and we stick it in between operators, and then this turns these operators into expectation values. And the reason that we do this is because expectation values commute, right? They're just numbers, so that means that we can shift things around in a nice way, and it will get our expression for the reduced system density operator in the form that we showed in the previous slide. So yeah, essentially we just shuffle numbers around since they commute. So here's how we're going to start. We're going to say that the reduced system density operator at time n is equal to the density operator of the composite system at time Tn, where I trace out the Bath degrees of freedom. And then what I do is I take my unitary time evolution operators for Tn time, at time Tn, and I say that's equal to just applying the time evolution for each time step n times. So if I write that out a bit more explicitly, I'm just shifting along the time axis one step at a time here, right? With either a U or a U dagger. And in between these steps here, what else have I done? I've also added in my assumption of a factorized initial state and a thermal state at the bath. So now I use my Trotter decomposition, where I take each one of these and I decompose it into, let me see if I can zoom. So I decompose it into the system, the bath and the interaction, and the system term again. I'll have to do. Okay, now what I do is I label each one of these groups of unitary operators. I'll label the ones closest to the state k equals 0, and then we'll increase k as we go out up to k equals n minus 1. And that means that I have these n times, which is what I want. I want to apply n number of times. And then my next step is just to resolve the identity at these different time steps with either the plus or the minus, depending on if I'm on the left or the right of the density operator. And what this does is it'll essentially put in a bunch of bras and kets around these operators, which will turn them into numbers, and that will allow me to shuffle things around. So at this point, we've given a pretty brief outline of how to perform this derivation. In order to get the matrix elements of the reduced system density operator at time Tn, with respect to the orthonormal basis formed by the eigenstates of the coupling operator at time Tn. And we said that basically if we move into the interaction picture, we can just ignore this free evolution of the system term, which then means that if we know the influence functional and we know the initial state of the system, then we can find the state of the system at any time. So this is really powerful, and we'll see why it's powerful now just by quickly looking at the terms within the influence functional. So this term here, HB, is the sum of the free Hamiltonian of the bath and the interaction Hamiltonian. And these states, here and here, and here and here, are just eigenstates of the coupling operator, right? So depending on what my interaction looks like, how my system couples to the bath, that is what this influence functional depends on. That's the only thing that the influence functional depends on when we're asking about the system. And why is that interesting? Well, it means that I can apply the same influence functional to describe the dynamics of different systems, provided that those systems couple to the same baths in the same way. And what does that mean? It means that if I calculate this influence functional for a particular model, I can apply it to a different model as long as the system couples to the bath in the same way. And this is basically the power of this influence functional method. And it gets implemented using something called a process tensor. And the process tensor is, I believe, just a representation of the influence functional as a matrix product operator, which we can then use tensor network techniques on to calculate and perform these calculations really efficiently. So this is the power of what this influence functional does, really. It allows us to quantify the effect of the bath on a system by only knowing the bath Hamiltonian and the coupling operator of the system with the bath. And what that then means is that we can apply the same influence functional to multiple different systems, provided that they are connected to the same bath with the same coupling operator. And by this, I don't mean that they're coupled to the same bath at the same time, right? I'm talking about one system coupled to a bath, and then we can just basically like swap out the system for something else. And as long as it is connected to the same bath in the same way, then this influence functional can be used multiple times. And that's good because it's really efficient. So this is basically why we're trying to find this influence functional. And specifically, the reason that I'm interested in it is because I'm calculating numerically exact work statistics for an open quantum system. And essentially what that boils down to is this influence functional just gets modified slightly. I'll make another video about it to explain how it works. But basically, all that I need to do to find the work statistics of an open quantum system is track its dynamics in a slightly modified frame. So imagine that we're in the lab frame, and then I move into the interaction frame, and then I move into a slightly different frame again in order to track these work statistics. And then I can just derive the influence functional in that second frame or that third frame. And then I simply get my work statistics out of that. So that's the reason why I'm interested in this. I might do a longer video showing the derivation exactly, like step by step, but it's quite tedious and also quite hard to write on a presentation like this. So I might type it up and then I'll go through it step by step in another video. So thanks for watching, and if anyone's got any questions, feel free to ask me, and I'll do my best to answer them. So thank you.